Yeah, thanks. Hello, everyone. Can you hear me?
Yes, we can.
Okay, good. My name is Ilia Yastrebov. I joined NVIDIA and UCX team 1 year ago. And so today I'm going to present cross-GVMI UMR memory key pool optimization. This approach and proof of concept was designed by Yong, and it was actually presented 1 year ago at UCF conference. And then in UCX team, we continued this effort. The proposed approach was refined and re-implemented and then committed to UCX master branch. And today in this talk, we discuss the capabilities and constraints of the solution, some details of the implementation, of course, performance results, and some future work. Please feel free to interrupt me anytime for questions or clarifications. So first, let me give you some context information. I'm not going to repeat what was presented already 1 year ago, so it's going to be a very short introduction, maybe. So with traditional server architectures, typically you have the host with all of its computational capabilities, whether it's CPU or GPU. They sit separate from the network, and the host side does quite a bit of work to progress communication. On the right side, we see that there is a blue field data processing unit, or DPU, and those are specialized infrastructure processors designed to offload and accelerate networking operations. And at a very high level, the DPU is a system on a chip that includes network core that connects X7 in our case with both InfiniBand and Ethernet. And this NIC is programmable, so it has CPU cores and memory and all the other hardware, so that we can run generic operating system, and we can build and run any programs on GPU using standard Linux tools and compilers. Basically, GPU allows us to overlap computation and communication because we can offload communication part from the host to the GPU. And yeah, by this, we can improve overall system performance and efficiency. And one of the most important features that we leverage from the Bluefield GPU is cross-GVMI memory key. This memory key, like any other InfiniBand memory key, is used by GMA engine to map between physical memory and virtual memory. But it is a very special memory key that also allows you to post network operations from the GPU side that will affect memory sitting on the host side. So, for instance, we can create a cross-GVMI memory key on the host side, and then create an alias to this key on the GPU side. And then from GPU side, we can post the work request referencing the host memory without actually without needing of the host involvement at all. And the principal benefit, what it gives us, is that we don't need to copy data from the host side to GPU. Okay, now let me show you typical cross-GVMI offloading workflow, just to better understand the components involved and functions being used. So on this diagram, we have two hosts, sender and receiver, and two corresponding GPU daemons. Each host has some user memory that we need to send between the hosts. And the workflow on sender and receiver is pretty much the same. So let me cover mostly the sender side. Here, what I want to emphasize, we don't have any UMR optimization yet. So first, we do a memory registration with UCP memmap call, and as a result, the direct memory key is produced. Underneath it calls IBVRGMR, and then what we want to do next is to export this direct memory key to the DPU side, so that it can initiate DMA operations on behalf of the host. So for that, we invoke UCP memh pack function with export flag, and underneath this call does two important things. It creates an indirect memory key, and then it allows cross-GVMI access on it. And as a result, we get a cross-GVMI memory key that we need to propagate to the DPU side. Once this memory key is received by the DPU side, we need to do a sort of import operation. Importing means we call, again, UCP memmap with import flag, and this essentially internally creates an alias to the host cross-GVMI memory key. And now sender DPU initiates RDMA operation using this green alias key, and then receiver DPU performs RDMA read operation using these two aliases. Actually, this operation copies the sender host memory into receiver host memory without host involvement at all. And on this diagram, I put just a single RMA operation, but there could be many of them during the entire application lifetime. And at the end of the data exchange, we need to destroy an alias on the GPU side, and on the host, on the sender host, and also on the receiver, we need to destroy the corresponding indirect cross-GVMI memory key. At the very high level, this is how it works. So far, all good. No issues. Let me come to the problem, just to state the problem that we are trying to solve. Here is the list of approximate cost of the core operations involved. So when we discuss the host side, there is an export operation that involves creating indirect memory key and then modifying it. So this is what we call export operation, and on average it takes from 250 to 350 microseconds. And there is appropriate import operation on the DPU side, which roughly takes 200 microseconds. And of course, you need to destroy this once those keys are not needed anymore. This overhead is absolutely negligible when we can use the same memory buffer across the entire application lifetime. Because in this case, cross-GVMI key and alias are created just once and reused many, many times. This is what we call a permanent memory buffers, or sometimes persistent workflow, or sometimes regular workflow. So the overhead of this memory key management is just negligible. But imagine that application uses many non-persistent memory buffers, and according to Yong, this is actually some existing workflow in several applications, especially during initialization phase. And in this use case, the memory buffer has very short lifetime. It can be used maybe only once, and then gets disposed immediately. And in this particular case, the overhead of cross-GVMI export and import operations can be very resource intensive, especially on small message sizes. Here is a table prepared by Yong that lists the performance or overhead of the involved operations in nanoseconds. You can see that on low dimensions, the cost of memory key creation and export can be in order of magnitudes higher than the memory registration itself. So the problem that we are trying to solve is basically to optimize this workflow with temporary buffers or non-persistent workflow. And the solution to this problem, it was proposed by Yong 1 year ago at the UCF conference. And the principal idea here is to leverage user memory registration or UMR. It allows us to do two things. So first, we can register indirect memory key through work request, which is very lightweight operation. You can look at this table. So here what I'm talking about is this. So registration is very, very cheap, and invalidation as well. It's very cheap operation and doesn't depend much on the message size. And second important feature is that we can actually reuse the same indirect memory key multiple times by binding it with different direct memory keys on demand. Once binding is not needed, we can unbind it. For example, when region is unmapped, and later on we can bind it. We can bind this cross-GVMI memory key again with something else. Based on these properties of the UMR, the proposed optimization is basically to optimize the cost of indirect keys management by reusing the same keys, so that on the exporter side, we reuse the pool of those indirect UMR keys, and on the importer side, we reuse basically the aliases, the hash map of those aliases. Okay. And with UMR optimization, the workflow that I showed previously, now it looks slightly different. Now, when we register a user buffer, we get a direct memory key, and we want to offload it to the GPU. We call UCP-MMH pack. And now, instead of creating cross-GVMI key, we just take it from the pool, or create if the pool is empty. We take this key, and then we register it with current memory region here using the API. We are going to discuss it later on the next slide. So we use this API to register or bind it, and then we send this key to the GPU side, and then on GPU side again we find or create alias in the hash map. So when we have a lot of operations, this is the cost of creation is amortized. So basically it ends up just taking it from the hash map. And then the workflow is basically the same until the end. When we don't need this memory buffer anymore, we call unmap, which internally unbinds or deregisters, or sometimes it's called invalidation. We unbind the memory region from cross-GVMI UMR key and just return this key back to the pool so that it can be reused in the next for the next operations. So here I list the most important design decisions, trade-offs. So let me quickly go through all of them. So first, this feature is enabled by default, but it can be also disabled with environment variable. We have a dedicated QP and completion queue on the exporter host side, and that's created on demand only when actually we want to export when on the host side we need to export something. There is a UMR MK pool on the host side, and initially it's empty, so we lazily create those keys on demand on the first use. And currently there is no any eviction policy, which means that those keys remain in the memory pool during the entire application lifetime. I don't know if it can be a problem. Like, typically there is initial burst at the startup time, and then we need to keep in mind that those keys remain in memory. And then there is appropriate hash map of aliases on the GPU side. Very simple structure. And again, there is no eviction policy. Yeah, so potentially this can be a problem if there is a long-living service or daemon on the GPU side, and there are multiple client applications connecting to it. Then we need to keep an eye on this because all those MK aliases are stored permanently and there is no any eviction. Then we need to support both old-fashioned non-UMR workflow together with UMR workflow to be backward compatible. And for this purpose, we mark all the UMR keys with a special tag to basically distinguish them on the importer side from non-UMR keys. So it's fully backward compatible in this sense. And zero-based virtual address. It was basically one of the most important design decisions. And in the Yong prototype, there was actually usage of zero-based virtual address feature. And it was used not because it's super useful or gives us some benefits. This decision was rather dictated by the API that was used for UMR registration, namely this direct verbs via MR list. That API supports only zero-based virtual address mode for UMR keys. And for UCX, this is a very serious limitation because currently it's not compatible with existing UCX memory key management mechanism, and it's going to be hard and painful to introduce a support for it, especially at the UCP layer. And basically, we were looking for options to get rid of this limitation, to get rid of this dependency. Several approaches were investigated. If you want, I can tell you more about this later. And finally, we decided to leverage verbs API for binding memory window, which is IBV, WR, bind, MW. This is implemented internally by sending a UMR work request that fills the data in memory key and its KLM. So by chance, it does exactly what we need. And just to clarify, we don't create a memory window, but we use a UMR key instead of the memory window. Looks maybe a bit hackish, but yeah, it works. What it does, it creates a single KLM entry, and subsequently the limitation is that this UMR key cannot handle regions larger than 2 GB, That's one limitation, and it doesn't support multi-segment memory regions or multi-threaded. In those cases, basically we resort to KSM registration, basically non-UMR MK approach. Okay. And then in the scope of this project, we implemented the daemon. That is a service that is basically an example of daemon service for GPU side. It uses active messages as a control messages to interact between host and remote GPU side. It supports reconnection, but currently it supports at most one simultaneous host application. So you cannot connect from multiple host applications. Currently support just one. It also handles tailed UMR keys, maybe not very important here. And currently it has several limitations. We can address them in the future. So currently it supports only active messages API and with 0 header size. It doesn't support tag matching yet. Currently communication pattern is unidirectional. And for this reason, latency tests are not yet supported. And we still need to enforce rendezvous protocol with environment variables that I list here. And currently, of course, it works only with host memory type. Very quickly, just to demonstrate those control messages. Those are active messages that used to control the workflow between host and daemon. Those messages are init when we need to initialize, when client host application joins for the first time, we need to send this init message to the GPU daemon. And by the way, there is also peer init, which I missed here. Okay, and then when we need to offload something, we send a send active message to the GPU, and later on, GPU side transmits the data using peer TX active message to the receiver GPU. And at the end of the call, it sends back to the host the completion. It's either send completion or receive completion on the receiver side. It's very simple. And now let's talk a bit about persistent versus temporary workflow. So as I mentioned before, persistent workflow is the flow when we reuse the same memory or user buffer for all performance test iterations. That means we create it once and use it over the entire application lifetime. And with temporary workflow, and as the name suggests, we create new memory region or new buffer for each iteration. We use it once, we dispose it immediately, and for the next iteration, we just repeat the process. We create a new buffer. But what's important, it happens only on the sender side. On the receiver side, we still do reuse the same buffer. And just to tell you, just for you to have an idea about performance of this temporary workflow, currently it's super slow comparing to a regular one. It's from 100 to 1000 times slower. Yeah, and probably UMR is not the only way we can improve this workflow if there is such a goal. Currently, this temporary workflow is not committed to UCX master. It can only be enabled by applying some patch. So if you want to test it, just ask myself. Okay, And this graph is not super interesting. Basically here we just test UMR approach with regular workflow. It means we create a single buffer and use it for all the performance iterations. And we just need this graph to understand if UMR approach brings some overhead to the regular workflow. So on this graph, on this diagram, there are three graphs. So the first one is host to host with regular workflow. The orange one is GPU offloading with regular workflow. And the last one, the green one, is GPU offloading with UMR optimization. And basically what we can see is that the UMR approach does not bring any overhead to the regular workflow. This is rather expected behavior. Okay, and that's the interesting part. So on this slide, we can finally see the benefits of UMR optimization. So it shines with temporary workflow. On these diagrams, there are again three graphs. So it's host to host with temporary workflow, then GPU offloading with temporary workflow, and GPU offloading with UMR optimization with temporary workflow. So now we see that GPU offloading with UMR optimization demonstrates significantly better performance, both in terms of the bandwidth and latency, and that's especially visible on small messages. Probably this is more visible on the right graph. So the results are really positive. And what's really interesting here is that UMR offloading case is even faster than the direct host-to-host communication. Why is that? Normally this shouldn't happen, right? Logically, host-to-host communication should be the fastest one. So it must be I'm talking about the blue line here. This must be our baseline, and it must be here below the green. But it happens like this because there is one more overhead applicable when we have direct host-to-host communication. Basically, when we pack our key for direct communication, we also create an atomic indirect key. Only if hardware supports it. And in my case, it's supported. And this extra call explains why host-to-host latency is actually bigger than offloading with UMR. Just because, this is not optimized case. We create this atomic key on the first call, and I guess this optimization is done to improve performance in certain cases. And obviously with UMR, we don't create this extra atomic key, neither on exporter nor or importer side, and that's why the latency is lower. Okay, so let's take a look at the performance breakdown and analysis.
Yeah, one quick.
Yeah.
The temporary workflow. So in the temporary workflow, is it the case that for each iteration, you just end up releasing the host buffers or like calling free? Like the next one, actually, when you were showing the graphs, right? Where you showed that host to host was actually slower than the DPU case. The next one, I think.
Yeah.
Yeah, here. So is it the case that in each iteration, you're actually releasing the host buffers?
Yes, of course. On each iteration, we release and we create a new one for the next iteration. Yeah.
So it would mean that like that packing, that atomic bit is actually showing up in the critical path for each iteration. This is why host to host is actually more expensive than the DPU with UMR. Okay, that makes sense.
Yes. Yeah, I guess we create this atomic key because, obviously we want to reuse it on the next iteration, so we create it once. But in this temporary workflow, reuse doesn't happen. So the overhead is added to this. this lane.
Okay, thanks.
Okay. So let's take a look at this performance breakdown. First, all the performance tests were executed with window size of 32, meaning that there are at most 32 simultaneous send operations triggered by the sender. And because of that, UMR key pool grows up to 32 elements. And obviously corresponding UMR hash map on the GPU side reach the same size. And on the left side of the screen, you can see the performance breakdown for GPU offloading without UMR optimization. And on the right side, the one with UMR optimization. So as expected, the cost of memory registration is equal in left and right parts. That's what's different is the cost of the export operation. So without UMR, the export cost is pretty much constant, around 350 microseconds, and slowly grows with message size. With UMR approach, the overhead of export is around just 4 microseconds, and in theory, it should not even grow above that. So I'm talking about this. So in theory, it should remain constant. And we just see higher values on large dimensions here, just because I was lazy, I reduced the amount of iterations to, I think it was 10,000 for 64 megabytes and just 1,000 for 1 gigabyte messages, just because it takes so much time. Like you have to wait for 10 minutes to run a single test. That's why, I mean, we see that the cost of the exporting is slightly increasing here. And the picture is almost identical on the GPU side, where we measure the cost of import operation. Basically, you can see that amortized cost of mem attach is almost zero, because we don't need to create a new memory key each time, and we don't need to destroy it. Sorry, alias. So we don't need to create this alias and destroy alias. So it's pretty much zero. So to summarize the results in absolute numbers, the latency is improved by 400 to 500 microseconds, which is relatively 2 times better on small messages. I didn't measure like tiny messages of 1 byte. Maybe it's also worth doing it. On bigger sizes, this benefit is almost negligible just because of the very costly memory registration. Okay, so that's mostly it. And here is the list of future work action items. So maybe we should implement simulation where cross-GVMI is not supported by hardware. Then what we also plan to do is to improve cross-GVMI so that it works out of the box. It means that we don't need to enforce, for example, rendezvous protocol between the daemons, so that normally it should work automatically. We had different ideas how to achieve that. And one of the most promising approach is to introduce a new memory type for imported memory. So currently there is a proof of concept that works, but yeah, currently this work is deprioritized. Then we can also think about eviction policy both on the exporter and the importer side, because we probably don't always want to grow these collections unbounded. We have some ideas on the validation of imported keys. And obviously we need some daemon improvements so that communication to make it bidirectional, to support latency test, and of course we need to support tag matching in the future. That's it on my side. Thank you for attention. Please ask me any questions if you have.
Do we have any questions online or in the room?
So I had one question. Sorry.
No, we're good. I'm muted.
So as it stands, is it the case that UMR is just used by default and we don't have to make a decision whether the application has a lot of use of temporary buffers or not? Is that the current policy?
Yes, the current policy is that UMR workflow is enabled by default. So whenever a host application exports some memory to the GPU, we use UMR feature unless those cases, unless you register very large memory segment larger than 2 GB, or you have multi-segment memory region. In those cases, we still use non-UMR approach. But for the rest, yes, by default, it's enabled.
For message sizes larger than 2 gigs, is it not possible to use multiple memory keys and pass them as a list of work requests?
Yeah, it's a very good question. So I'm sharing this backup slide. So currently we have this limitation because we use this API that I'm highlighting now.
Right.
And internally it creates just one KLM entry, so it cannot, I think it cannot be easily modified. But when we discussed this approach, we considered different alternatives. The one that is implemented is this one. But ideally, what we discussed initially, we would need to implement maybe some kind of DevX work request. It's also not, it's not an easy task, but it exists in the past in the experimental verbs prototype. So it can be done. We can attach a list of multiple KLM entries, and this way we don't have any limitation on the region size. So it's doable, but it's quite some effort to implement that. And for now, we just decided to reuse what is already provided by Verbs API. In the future, if there is a need, if there is enough interest in this feature, we can go this way and implement maybe DevX version of this registration. Okay.
One last question. Are there any restrictions on what kind of QPs you can use with UMRs? Or does it, is it allowed with all sorts of QPs like RC, DC, and others?
I think it's allowed on all sorts of QPs, but the simplest, I'm not sure about UD.
Okay.
The simplest is out of QP.
Okay.
I think there is some limitation that I found here. Okay, there was a huge diagram here. Like Yossi said, I'm not sure about UD. There was a table. I think I will not find it right now.
Yeah, I don't think it's okay to share this document in this meeting.
Yeah.
Okay, good to know. Thanks.
Do we have any more questions? There's a comment from Steve Paul online that he really like your work. So thumbs up.
Thank you.
Okay, seems we don't have any other questions. Okay, there is a question from Oscar. Approximately, what is the overhead of second option with first option?
Okay, let me share again. Sorry. Just share. It seems. I'm sorry, but what options are we talking about? Are we talking about these two options?
Yes.
It's hard to say without measurement. I guess the overhead will not differ a lot because ultimately those should be basically almost the same operation, because here we just create UMR segment, then create a UMR control segment, then UMR segment, and then data segment. So ultimately, whatever way we implement this, it will be just creating the same work request, very similar. So I don't expect significant difference in terms of performance, but the complexity to implement it, now I don't remember all the details we discussed before, but it's not going to be a simple task because we need to modify quite a lot of internals for that.